Welcome to Tollefson Physics. So what we're going to look at today is how we apply Newton's second law to relate forces to acceleration. So in this particular case, we're going to specifically look at what's happening in an elevator. And so we can make measurements on an elevator to actually be able to calculate what is the acceleration on the elevator. And so one way to do that is to stand on a spring scale, which is, we'll just call it a scale. And so instead of having a scale that's reading in pounds, we're going to look at a scale that is reading the force in newtons instead. And so let's look at this problem that we're going to look at. So we've got a student that stands on a scale in a stationary elevator, and initially they have a force, the scale is reading a force of 500 newtons. So because they're not accelerating, that is actually their force due to gravity as well. Now what the scale is reading is the normal force. But since you're in equilibrium, the up force has to equal the down force. And so therefore the weight of the individual is 500 newtons. They push the down button, so they're up on a high floor. They push the down button, it's going to speed up and it's going to go downward. And now the scale reads something less. And so that scale is reading 450 newtons. So we're going to figure out what is the acceleration of the elevator as it speeds up in the downward direction. So what we're going to look at first when we're dealing with forces, always a good idea to draw a force diagram. So when the elevator wasn't moving, we were at a force of 500 newtons, which was the normal force at that time, but as I said, that is also the gravitational force because there's no acceleration. But now that you hit the down button, the normal force, which is what the scale reads, changes to 450 newtons. So now we have a net force because it's speeding up in the downward direction. How do we know it's speeding up the downward direction? Well, I said, but also the downward force is larger than the upward force. So we can simply use Newton's second law, and I'm going to write it this way as the acceleration equals the net force divided by the mass. And so in this particular case, what is the net force? Well, since my direction of acceleration is down, the direction of acceleration is down, well, then I'm going to have my coordinate system face that direction too. So technically this is the plus direction, that's the minus direction. And so because of that, I'm going to say my net force is 500 newtons in the downward direction minus 450 newtons in the upward direction. And that's all divided by the mass. So what is the mass? Well, just off to the side here, force of gravity equals m times g. Right? We're going to use g equals 10. But I want to know the mass. So mass, if we divide both sides by g, is that force due to gravity divided by the gravitational constant. So in this particular case, 500 newtons divided by 10 newtons per kilogram gives me a mass of 50 kilograms. So I'll put that back up here, 50 kilograms. So if we do 50 minus 500 minus 450 newtons, that's 50 newtons. Divide that by 50 kilograms, I get an acceleration that is 1. And so with the units I've written, it's actually newtons per kilogram, but more customarily when we're dealing with motion and distance and time, we're going to write that as 1 meter per second squared. These are equivalent units. All right, so that's the acceleration in the elevator when we're going down. So actually I could write the direction, it's down direction. So instead of being ambiguous with what I called plus and minus, let's just say it's in the down direction. So now let's take that to when that elevator slows down as it gets to the bottom floor. And so as it slows down as it gets to the bottom floor, this says the scale now reads higher. It's 600 newtons. So I'm going to go ahead and draw a force diagram. So the force due to gravity of that person doesn't change because their mass didn't change and they're not on a different planet. And so the normal force is what the scale reads, and so the normal force is 600 newtons. Well, you got to think about it. You're traveling downward. To slow down, the acceleration has to oppose that, and so that's upward. So the coordinate system that I pick is up is positive, down is negative, because I like my accelerations to always be positive, personal preference. So acceleration equals F net over m. And so in this case, we're going to take the big arrow minus the small arrow, the up arrow and the down arrow, and divide it by the 50 kilograms that we figured out before. And so 600 minus 500 is 100 divided by 50 gives us 2, and I'll go right to meters per second squared. And in this case, that acceleration was in the up direction. So now it's your turn. A slightly different elevator question. We have so we're going to, instead of having a person standing in there, we have our elevator like this. We have a spring scale, and we have a mass hanging on the spring scale. And so the spring scale is going to read the force. This is just a different way to measure the force. And so it's going to change depending on what's happening. So in this particular case, we're at the ground floor, just kind of where we just left off. We have this 1 kilogram mass hanging on there. And so when you hit the up button, the spring gauge goes from 10 newtons up to 12 newtons. So from that information, I want you to determine the acceleration of the elevator. Pause the video now and resume when you're ready to see the result. So when we're dealing with a force type question, usually a good idea to draw a force diagram. So I'm going to go ahead and draw a force or a free body diagram. So 1 kilogram, as I kind of inferred before, is 10 newtons. Right? That's based on the gravitational constant. And the spring gauge is pointing upward, and it's reading 12 newtons. So from that, I can calculate the acceleration based upon that data, F net divided by mass. So in this case, my up force is the bigger force, my down force is the smaller force, and I'm going to divide that by the mass, which was simply 1 kilogram. So 12 minus 10 is 2, and divide by 1, it's still 2. So the acceleration in this particular case is 2 meters per second squared, and it's accelerating up because that arrow is the longer arrow. All right, so keep working on these kind of questions and you will be able to do better.